are gathered here today for the training for the DektakXT Stylus profilometer. And we have here with us, we gladly have an expert from Bruker. He is Dr. Ole Göbel. He is the field service engineer from Bruker Nanosurface Division in Karlsruhe, Germany. All right. So a little bit about Dr. Göbel. He received his diploma in Mineralogy from the University of Kiel, Kiel in Germany, and his Ph.D. from Groningen in Netherlands. And then he worked on some organic precursor solutions, and since 2011 he is the field service engineer at Bruker Nanosurface Division. So he is servicing AFMs, tribometers, profilometers, and organizing such user trainings like today. So without further ado, please welcome Dr. Göbel. Thank you.
Thank you very much, and then also from my side, good morning, and thanks for your interest in coming here. To be sure, I'm one of the field service engineers. I'm not the only one, right? Otherwise we could not manage this. Okay. I think we should say maybe the program that is on the board or that has been announced would be slightly changed. There will be no general introduction or demonstration in this room like we were intended we were intending to do. It would be rather, I would just give an introduction on the system itself and on the process and on the method, and then the rest will be hands-on. So I think you all have been split into groups of 5, and after about half an hour when I'm done, we would go downstairs with the first group and then spend rather more time in front of the instrument than here. I think that is more fruitful. Yes. And then I believe some of you brought samples. I think we can schedule at least 45 minutes per group, so there should be enough time. 45 is realistic, right? 30, 45. There should be enough time then to measure a few samples of yours, and everybody should have the chance to press some buttons. Okay, so I took, I'm giving trainings for customers, but I'm not usually giving presentations like this one. So I took the presentation of colleagues of mine and deleted a couple of slides where I think like this is not really interesting information, such as the history of the DekTak. So I'm none of them. They are responsible for the slides that you see here. All errors you blame on them, and you just we just go ahead. Where's that button? So I would just say a little bit about the profiling method. I think the purpose of this training is everybody knows what system is standing downstairs, everybody knows what it can do, and has some idea of how much work it is or how easy it is to use it. But in the end, everybody who wants to measure will still get a dedicated training by the staff. But the purpose here is to show you what can it do, how does it work. Yeah. So I speak about profiling and mention briefly what kind of tests we can do, and the method is the most important thing, and show you just a little bit of the hardware, which is probably not so exciting. So it's a profiler, or it's a mechanical profiler or a tactile profiler. Means like we scratch with a needle over the sample. So and that is a tactile method, but it's also a profiling technique in the sense that we image the surface of something on a rather large length scale. Larger length scales than what the AFM can do, which I believe is behind the screen here, and more in the range of other profilers that would be like what is shown here from the Bruker, from the house Bruker, white light interferometers, optical profilometers. But what we will see downstairs is the tactile profiler, this machine. And there's always like a comparison, optical profiler or tactile profiler, what is better, what is worse. The price is one thing, and the advantages and disadvantages otherwise are listed in this table. So the optical profiler has the big advantage that you don't touch the sample, you will not leave any traces on the sample, you will not manipulate or damage the surface. It is a faster method. But the optical profiler has of course large problems with, or certain problems with transparent samples. and it is also not so well recognized by industrial standards as is the as you would have with the contact profiler. So what does it do? We scratch a needle over the sample, or strictly speaking, we move a sample underneath the needle. We record the surface of the sample, and then we can determine or analyze the measurement in various ways. We can, that's what we will do here in the main place, determine the step height of a step, and we can determine the roughness. We will not do the waviness, but the roughness of a sample. Other applications would be measure curvatures of certain things. That is more complicated and probably also not of interest, as I was told, for this university or this lab. So the way to measure the surface or the profile is roughly being described here. We have the sample resting on a scanner, and we move the scanner with the sample over a reference block, which is a very smooth or polished glass block. Any features on the glass block would lead also to an artificial bump in the surface profile, so it has to be a very smooth glass block. And then we pull the glass block with this, pull the sample with resting on the scanner over the glass block underneath the needle, which is called in the Bruker terms stylus, which can move up and down and then measures the profile of our track. And the way to measure the height of the stylus is by an LVDT sensor, a linear variable differential transducer. So we have the transformer, the LVDT transformer, we have the diamond tip on the stylus, and we have the moving stage on the reffing surface. Yeah, these are the components. And to explain it, I made this drawing here. Inside this measurement head, and you will only see this case here, downstairs. Now you can see it open, and inside of that head you have the schematic drawing here of the measurement bridge, which is the main part inside, which is shown here as the blue, and this yellow part, which I have drawn here in black, all in black. So we have a long beam with two rods at each end, and there's a magnetic core on each end, and that falls into coils. And the whole beam is resting on two short vertical arms, which end in little sharp needles, and they rest in little like bowls of hard metal bowls. So that forms like two bearings, and then the whole unit can wiggle up and down. And coupled to this measurement bridge is the stylus. It's a very long plastic beam, and at the end is the diamond tip. So the sample will move here, and the diamond tip will go up and down. We press it in a controlled way onto the surface, and then it will go up and down and will make this bridge wiggle. And then we have one of the cores. So that's what you can see here as well. You have the beam and the cores in the coils, everything drawn in blue here. But the crucial point is now one of the cores is in a coil, and if we apply an electric current onto the core is being sucked into the coil, and it will move. The whole bridge will be pulled in this direction, or will tilt in this direction, and will push the stylus down. So this is the force coil. So if we adjust the current through this coil, then we control the force with which we press down the stylus on the sample. And then as the whole bridge wiggles while the sample moves, this core falls into two coils, and then depending on the angle it falls more onto this or onto that coil. So it changes the inductivity of the two coils, and then by comparing them we get a very precise measure for the tilt angle of the measurement bridge. And that is what then is the differential or variable differential transducer. So that is our high precision. Well, strictly speaking, it's a position sensor for the core, and then it can be also, it's been used as a position sensor for the tip, for the stylus. So that gives us then the height information of the stylus, which is the profile. Okay, that is the principle. This is how it's being realized by Bruker in the DekTak. We have the measurement system itself for the DekTak. We have a computer with a screen and a power switch on and off. And the heart is this, you can see here, is the scanner, which we see here resting on this scan block. And we move the scanner with the sample back and forth. Now in this drawing here you see like a wafer chuck. Downstairs you will find a simple metal block onto which you put the sample. But that would be exchangeable. Now you have a power supply and you have the stylus in a nice case. You will not change the stylus, you just see it as it is mounted in the instrument. Yeah, to show you a little bit of the software that you will expect, that you will see in a while, you can set the scan parameters with one button and say like, I want this scan length, I want this duration of the scan, and I want this and that force, and I have this and this stylus installed. You can set up the units that in which you get the height and the length. That is probably not so exciting. The workflow is more exciting or more interesting. So you would place a sample, you would lower the stylus onto the sample, you would set your parameters, like I've shown before. You navigate to the exact place at which you want to start the scan. You make a couple of scans to level the surface nicely, because the software can, we always assume that we have a straight, flat surface, so the profile should be approximately a straight line unless there was a step, but there should be always straight components in our profile. And if you place a sample in the first place, it will never be the case. There will always be some tilt in the sample. Now the software can correct for this, but as it goes, software correction is always introduces errors, so it is always the best to level the surface mechanically as good as possible. So you do like some preliminary scans of the sample and adjust the leveling mechanically with an adjustment knob, which was I think actually shown in here. So you just spend a couple of minutes, no, not a couple of minutes, but like a minute or two in adjusting the leveling of the sample, and then you start your scan. And when the scan is done, the actual scan is done, the software will always switch to the oh no, sorry, there's one step too fast. So always when you scan, you can follow it on the video screen and you can see the live plot of the profile. But when the scan is done, the software switches to the analysis window, and then you can start to manipulate the data. Means like you do software leveling, hopefully as little as possible, but as much as needed. And then you can analyze or draw the information that you're interested in. So we will do today step height and roughness. And I was told that was the main tasks of this instrument, or the main purposes for this instrument. Step height, I don't need to stay much here because that is pretty straightforward. At the end, I will say a few words about measuring roughness according to ISO standards. So the software that or the view that you will see downstairs, or the analyze window that you will see downstairs will look slightly different than here, but principally it gives you an idea. You put cursors, you say level the profile between these two cursors, and then you can do roughness analysis, step detection, or step height calculation. I think that is a little interesting. Rather say, sorry, I thought I had deleted all these slides, but obviously I hadn't. This is relevant. As you can imagine, the radius of curvature of the stylus plays a role or determines the resolution, both the vertical and lateral resolution of our profile. So downstairs there's at this moment there's a 12.5 micron radius stylus installed, but in the drawer there's also a 2 micron radius, which would be the one that you would use for getting short wavelength roughness measurements. There are more styli available, or more types of styli available. yeah, I think we take a note. Of course, if we want to get the maximum of data points, or the maximum or the best resolution, we don't only have to use a very sharp stylus, we should also use a lot of data points. I mean, there's a limit, there's a maximum of what makes sense, but and that determines also, and that maximum is also determined by the software, how many data points in total we can collect. But in general, it means that you have to reduce your scan velocity drastically to get enough data points for a decent roughness calculation compared to a step height measurement in which you can measure much faster. I will explain that downstairs when we are there.
Ole?
Yes?
What is the smallest stylus?
Oh, you looked it up yesterday,
Yes.
right?
A nanometer.
Ridiculously small. Yes.
The minimum usable, they say, it practically is 0.2 micron. There is 0.1. It can be used.
What we
Yeah.
have here is a 2 micron.
A 2
The smallest one we have
micron.
here is 2, but you can go to 0.2.
Yeah, downstairs
This is
two.
only for
Roughness.
roughness measurements.
Roughness
If
measurements.
someone is really interested just to study,
Okay,
Roughness.
but the smallest stylus will detect the smallest resolution in the roughness.
Of course, yes. But the smallest stylus has the largest, with a given force, with a given load, has the highest pressure on the sample, means the highest chance to scratch into the sample. And at a certain time it will be just like a razor blade rather than something sliding over the surface. So I think with
What's the
the...
compromise between
That's a
what we
compromise.
detect and what
Yes.
we can use?
Yes, I mean, if you have metal samples, probably you're fine with you can operate with a sharp stylus. If you have plastics, probably that will not be a good idea. The minimum force that we can apply with the system downstairs is 0.03 milligrams. But then you can still calculate what does that mean on a radius of a few nanometers. Yeah, it will still be pretty high pressures. So I think with the 2 micron stylus downstairs, you're already pretty good for most roughness measurements. And then at a certain time you can say, like, maybe it's better to use an AFM than a profiler. Oh, sorry. So yeah, speaking about the, okay, I mentioned it, the stylus must be kept clean. So very important is when you use the instrument, make sure that your sample does not leave any dirt on the stylus, because it would just make it blunt. Also don't make sure that your sample is not so hard and your force is so high that you damage the stylus. Then you suddenly have 50 micron radius. But for example, what I see often is that people scan uncured photoresists. Yeah, then at a certain time you have a stylus with the size of a football. That is something to be aware of. I think there is a table here of all the styli available. I mean, right now the presentation is not ready to give away, but I can leave it behind, and there you have like an overview what is there. Very important to know, maybe to some degree it's important, is the cone angle of the styli, which is in one case for the 2 micron stylus we have a 60 degrees cone angle, and for the 12.5 it is 45 degrees. Does it play a role? Yeah. If you have features with very sharp slopes, then it might be important that you realize that you cannot fully perfectly image the profile at these slopes. I think that is shown also in the next presentation. So with the 25 micron stylus, we can image shallow and wide trenches very well, but high trenches or very narrow trenches, you get measurement artifacts. It's a consideration if you happen to have such features. I think also, yeah, is there something to say about it? Yes, what is important, it points us out. I mean, here it's called maintenance. I would rather call it things to be aware of is, as I said, we slide the scanner over the glass block, and any positive feature or any hill or mountain on the glass block will lead to an upward motion of the scanner and then also of the sample surface, so we get an artificial peak on our profile. So if you see that the glass block is dirty, then you should not measure, you should just make sure that it gets cleaned. And likewise, the stylus needs to move freely up and down, otherwise it cannot measure, otherwise the force will not be correct or the motion will be impeded, and then you don't get the proper profile. So one way or one possibility why the motion of the stylus can be wrong is it's not properly installed, or somebody bended it or pushed it. Maybe somebody pushed the shield sideways, and if you see that the stylus is touching this shield, or this you cannot maybe really see it. It's like a tunnel, and if you see that the stylus is touching on the side of it, then it's pointless to measure. It needs to be fixed first. I think this is why I kept these slides here.
So
Yeah.
it's very essential for the cleanness of the sample. The sample should be very clean, because you can easily damage the stylus tip, which is very expensive, and you can easily damage the glass, where the glass block, where the stage is moving. So it's very essential to have a clean samples, and for some reason, if you have dropped something on the stage, it's very essential to report to RANIA, or to want to clean, not use the system before, because this can easily damage the stage or the stylus.
Damage, well, contaminate, I should say. Yes, you can, it's not, I mean, you can clean it, then it's fine again.
But
The stylus can be damaged, the glass block, yeah, can be damaged only with brutal force, but it can be easily made dirty if dust particles, or if you have brittle coatings and parts chip off and fall onto the glass block. That is not good. I think cleaning the sample with some nitrogen or air is always a good idea. Okay. Okay, so I mentioned step height is pretty straightforward. I don't need to, I would show it downstairs. Roughness, according to ISO norm, is a bit more complicated. I've just explained the process now, but if you find the time, we will also do it downstairs later. So there are certain rules for the roughness measurement according to this ISO norm, and I believe on the next slide it's mentioned explicitly, DIN, IN, ISO, God knows. Everybody can do what he wants and call it, this is my roughness, but if you want to follow this norm, you have to follow this process flow. So you would just scan and tell the software, put cursors on your profile and say, like, calculate the RA or RZ or God knows roughness between these two. No, sorry, I should say, like, first you level. You put the sample, scan over certain lengths, and level, and then you use one of the filtering or one of the filter methods that the software provides, and you say, calculate for me the, say, RA. Say, like, this is what I'm interested in. And then you get, I'm going too fast here. No, we should follow the flow. You scan over certain lengths, you go to in the analyzer window, you pull from your toolbox, software toolbox, a tool which is called filtered roughness, put it in the flow, and just determine approximately the roughness. And you will get a value. You make sure that your filtered roughness is set up correctly by setting the right filter into it, which is a Gaussian filter. There are more filters. If you use the Gaussian regression filter, I think it gives more or less the same result, but the norm demands a Gaussian filter. You have an idea of the roughness from this calculation already. Then you go into the table. Well, an idea, you get a value, which is not the correct value, but it's close to the correct value. Then you go into this table and say, like, I have an RA roughness of something in this range. So I need to use a cutoff length of this value, and I have to have a scan length of 5 times this value. And then you go back to your software and adjust put the cutoff wavelengths into the filter, and you adjust also the scan length to 7 times the cutoff wavelength. Don't ask why, this is how it's defined. And then you measure again, and then you would get the correct, paste the cursors properly on 1/7 and 6/7 of the scan length, and then you get the roughness between the two, on the central 5/7 between here and here, the central 5/7, you get the roughness of your sample. This is the process. It's a bit lengthy, but it is like this. I think we have time to go through it, probably not with the 2-micron stylus, but with the 12.5. Well, I mean, we just do it for the practice and not for getting meaningful results. And I think that is it. Questions?
What is the range of the thickness you can measure?
Oh, good point. Very good point. So the stylus can probably move up to 2 millimeter up and down, but we can use our LVDT sensor allows us to measure displacements of 1 millimeter. So maximum height that we can measure is 1 millimeter, but we have this analog signal of the LVDT sensor is converted into a digital one with 65,500 something bits. And these 65,000 bits we can spread over 1 millimeter, over 524 micrometer, over 65 micrometer, or over 6.5 micrometer. So this determines then the answer to your question is 1 millimeter. Then adding additional information is we can have angstrom resolution because we have 65,000 bits, and in the smallest height range of 6.5 micron we spread 65,000 bits over 6,500 nanometer gives us 0.1 nanometer. It's like 1 angstrom.
So it doesn't depend on but it should depend on the radius of the tip.
No, the height resolution does not depend on the tip radius. Well, the height resolution in general, if we have a step, it's always fine. If we have trenches, then indeed our height resolution is dependent by the radius of the stylus. But that's then because it is a step and not because of the hardware.
So it's plus minus 1 millimeter or plus minus 0.5 millimeter?
In total 1 millimeter.
Oh.
So you can set up, there are 3 types of profile depending on when you bring the stylus down onto the sample, you can choose whether you want to lower it such that it can move 50% of the height range up and 50% down. So that would be 0.5, 0.5, or whether it should go 90 down and 10 up, or vice versa, 90 up and 10 down. These 3 possibilities are there to spread it, but 1 millimeter in total maximum.
So we can't use a sample thicker than 1?
Well, sample thickness is not crucial. You can put samples as thick as you want, as long as they fit, but height differences larger than 1 cannot be measured. Cannot be measured, well, there's still a little bit space of movement, but I don't know how much it is actually. You should make sure that it's not higher than 1 millimeter, yes. Probably 1.1 is also fine, but you will not measure it anymore.
Few centimeters.
3, 4 centimeters.
Yeah, the sample height or thickness of the sample in total is not relevant, as long as it fits under.
So the sample is deposited on a glass slide, for example. Doesn't mean anything.
See the variation until they see it.
يعني من أول نقطة لأعلى نقطة. 1 millimeter.
مش مهم شو السامبل.
Yeah, you said it like about this is the maximum height, I would think.
No, it's not.
Yeah, well, not yours, but if somebody comes from...
Slide, there's a film on the glass slide.
Yes,
So we're measuring the...
your samples. But indeed, if somebody comes from mechanical engineering,
Maybe it has 3, 4 centimeters.
Yes,
why
yes,
not?
It can fit?
yes.
it can fit, but I think the maximum weight that we specify is like 3 kilograms. Or maybe less, sorry, take it back.
We
one and a half, I believe. Yeah, you cannot put a whole crankshaft there.
Yeah, sure.
For the roughness measurements,
Yes.
you're always measuring a line.
Always a line.
Always a line. So if you want to integrate over, say, a surface, can you automate it to measure several lines? And you know what I mean?
I know what you mean. Yes, yes, and the answer is no. You cannot, because you can measure on different positions of the sample, but the software cannot stitch several lines together. The software can only do that if the hardware allows for motorized lateral motion. But this has a manual stage, so the software only can drive one motor, and it can only make a single line profile.
It
Well,
can be upgraded.
Sorry?
It can be upgraded to automatize.
Yes, it can be. I think it's painful, but it can be done. But you can export the profile as an ASCII file. If you have the right profile, if you have the right software, I'm pretty sure there's software which would allow you to put several line plots side by side.
So we can do it manually and then
Behind-
extract the data to reproduce a kind of an image.
No, Bruker allows you to make a line profile and to export it as an ASCII file. What you do with that ASCII file is not the business of Bruker, but I expect that there's software which allows you to put several line profiles side by side and construct a 3D surface. But I'm not, I guess, I'm not good with software, I don't know. But I was,
You will need so many points.
The problem is that when we first put the specs for the instrument, we put the specs for a 3D, and we sent it to everyone in the chemistry and the physics department, and they all decided they only want 2D. So we reduced the specifications only to 2D to have it all in emails. So
That's good. Okay.
we could have bought a 3D from the first place.
Would have probably been more expensive.
But anyway, not much more, because if you want to upgrade it later on, it will be much more than if you buy it at 3D in the first place.
That's fine, but then the roughness has to depend on the size of the stylus.
yeah, well, I mean, it depends on the wavelengths of your features. I mean, you can have high roughness with gigantic wavelengths.
In terms of limiting resolution.
Yes, well, yes and no. I mean, I think you can have gigantic roughnesses if you go into a mountain range. You don't need to have a super sharp stylus to measure this huge roughness. But typically, yes. I mean, usually if you have small features, small samples you can have very small features in nano engineering, and then you need a very sharp stylus to resolve them and to get the proper roughness. Yes, but okay, yes, the 2 micron stylus, and if needed, you could buy even sharper ones. I would say try it out with the 2 micron, and if you have the feeling that you don't get, or your roughness is too low, well, then it's worth to try maybe with a sharper one.
So the tip has to touch the sample.
Yes, tactile method.
So if the sample is not dry,
It should be dry.
Then it's the wrong method. As I said, you have to have a dry and hard sample. Oh, well, hard. It has to be dry and not sticky.
Contaminate if it is touching the sample.
Stylus, you mean? It will be contaminated.
Yeah, the stylus, well, you can clean it in alcohol.
لا مش أنت. The engineer will clean it all.
We will clean it for you.
Not the user, for sure.
The tip is very small and it's touching the sample.
Yeah, but
So
try,
everything in the sample.
but anyway, you have to be careful that your sample must be as dry as possible.
It is a dry gel. If you have a dry gel and you scratch it with anything.
There will be some deposits on
Yes.
the stylus. Yes.
What gel is it? Can you first of all, can you clean it afterwards, or is it some?
It's a gelatin gel, a dry gel.
So it's
Like
dried.
a film of dry gelatin gel.
Yeah, but even if it
There are
was,
reactants inside, so there are ions inside.
yes, well, it's a diamond. I mean, you will not damage the diamond by gel. You will only deposit. Worst case, you deposit something on it, but if it's gelatin gel, you can probably dissolve it easily.
So we clean.
You can clean it. Worst case, the
Clean
sample.
one.
the sample, the measurement may be bad, but you don't damage anything, or the contamination can be made
You have
undone.
to adjust it to touch it, but not scratch it.
You cannot.
The
I
system
mean, it needs to touch.
You don't do
you
anything.
don't do
Just
anything. Press the
say to
button.
load it, you load it and make contact by itself.
I should have said this, or maybe I didn't show the slide. You adjust the force. By applying, you tell the software use so and so many milligrams of load, and the minimum load is 0.03 milligrams, and that is pretty low. And if you, okay, maybe for your
This
case,
is the lowest in the world, I mean. The minimum.
Yeah, we always adjust the
No,
force.
No,
you
you
can
press it in the software.
parameters and parameters.
Yeah, you try, for example, your sample is hard, you can use 1 milligram on it, or 2 milligram. If it is quite soft, you have to reduce the force, not to scratch your sample. You can, if in the first run it scratches your sample, then you reduce the force and try again.
You can try with
You
the
can
lower
try directly
forces
with the
first.
lower force.
And then start.
Even if
to
it
increase.
scratches there,
Is that-
خلاص أنا.
ما كتير قصة اللور فورس دايما بتزبط يعني. في compromise.
She has a sample. and
yeah,
she
we're
uses
done.
the
We're just discussing things.
I guess she has a question.
It was asked already.
Ah, okay. Because I see.
بس قلت لك إيه فاهمة.
Any more questions?
What about lateral distance? You may have said it. How long can it
No, good point. I haven't said it. 55 millimeter. Was it 57?
Well,
55, I believe.
55 millimeters.
55 millimeter.
So that's about 2 inches.
I don't know.
Almost.
No, because I'm thinking of like measuring curvatures of wafers.
Yeah, but the sample chuck is not really good for. Oh, how much is 55? Yeah, you could place a sample of a small wafer on it. Yes, you could. The problem with wafers is always they're never perfectly flat. So you would, and if the wafer wobbles during the scan, you get, of course, nonsense values. So you would have to construct a holder for the wafer. And what Bruker is just doing for the wafer chucks is you place 3 little steel balls inside in the chuck that just come out of the surface, so the wafer is resting on 3 points,
So
and then it's
kind of
stable.
clamped, so that it doesn't-
Well, it's not clamped,
Almost.
but it's resting on 3 points,
I see.
and then it can, no matter how uneven the bottom side of the wafer is,
I see what
it
you're
will always
saying.
be
It's elevated in a way.
yes,
Oh, I see.
resting on 3 spots. So it's you create some artificial curvature. Yeah, okay, that's the point. How do you get rid of that? I don't know.
No, we usually do before and after.
After coating.
Yeah.
We discussed that yesterday. Yes, the software allows you to subtract 2 curves from each other and determine the change of curvature. But we said like the chuck downstairs would have to be manipulated, or maybe have to be replaced by something. I think it's not rocket science to construct a chuck with 3 balls or with 3-point bearings, but it's not there yet. Are we done? It looks like.
Thank you.
My pleasure.
Ole.